local gauge transformation. Each one of these F's transforms like G, F, G inverse, but then properties of the trace, the G, G inverse in the middle cancel, the G, G inverse on the outside by properties of the trace, cancel out by the, it's trace, you move it around. So that pure gauge term is already gauge invariant. And that's the other claim, is that this piece up here is also gauge invariant because we've traded the partial slash for the D slash. The D slash involves A. And see, the way A changes under a gauge transformation is this. And that is constructed in just such a way such that when you do a gauge transformation, like I've outlined here on this new introduction of A somehow makes this piece go away. It's not entirely obvious why that should happen, but you can calculate it, and it works out. Now, of course, that's lovely. Okay, great, so you're adding things to make other things cancel out. Why are you doing that? What happens? So, long story short, the total Lagrangian for this spinor gauge theory, it's a spinor minimally coupled to the Yang-Mills field. So you take the L psi plus the Yang-Mills term, that gives you the total Lagrangian. Your Lagrange equations look something like this. Delta, he uses a delta for variational. That's probably better than me. My notation earlier today. Because this is a variational derivative. So these right here, guys, this right here, those are the Yang-Mills equations. What do Yang-Mills equations look like specifically? They look something like this. D mu F mu nu equals to J nu. And what else? You also have this relation, D nu J nu equal to 0. That's covariant conservation of the non-abelian gauge current. In electricity and magnetism, this is an exercise I would certainly assign on a test if I was teaching it. You can prove this. This is true for Yang-Mills, for ordinary electromagnetism. This is conservation of charge. Because what this means is partial rho partial t is equal to the divergence of the current density. So this is that equation. And what that equation says is that the charge flowing out of a particular locale is equal to the change in charge at that locale. In other words, charge is neither created nor destroyed. It just moves around. And that equation says that non-abelian charge moves around. It's covariantly conserved, at least. So anyway, the Yang-Mills equations are different than Maxwell's equations because, well, there's that extra term there, right? You see it? This piece right here means that the Yang-Mills equations are different than Maxwell's equations. There's extra things. So this ends up producing, it ends up making the Yang-Mills equations nonlinear equations. In contrast, Maxwell's equations are what? I think they're linear. But anyway, that is a very madcap and poor introduction to Yang-Mills theory from a physicist's perspective. I'm giving you a rough lay of the land, which is we discovered basic gauge theory by studying electromagnetism, especially Weil's work in 1929, where he understood you could derive regular Maxwell equations from looking at like a complex, by looking at a scalar field, a complex scalar field, with a local gauge transformation. And then studying what would it take, what would you have to do in order to maintain the invariant of the invariance of the Lagrangian? Well, if you add a gauge field, gauge potential rather, a gauge potential field A mu, such that it transforms in the less complicated way for a while, then that prompts you to add another term to the Lagrangian, which when you look at it, tilt your head and squint, you realize it's that minus 1/4 f mu nu term. So basically, by studying a local gauge invariance, Weil showed that in their viewpoint, it necessitated the introduction of a gauge potential field, and then consequently the introduction of the field strength. So, the principle of studying a local gauge for classic, scalar field theory is in some sense giving you some kind of ad hoc derivation of electromagnetism. It's really kind of shocking that such an argument can even be made. I mean, it's a physicsy argument, so it's not, like something we're going to do in Math 200 or whatever, but it still has merit. And then what's very interesting is about, 30 years or so pass, and then Yang-Mills come along and try to do the same kind of thing, but for a non-abelian gauge group, right? And then they realize that the gauge transformation for the gauge potential has to look like this, and also the field strength has to have another thing added like that. This is interesting and different extensions of what was already done. But all of this is being done to maintain invariance of a Lagrangian with respect to a local symmetry transformation. Right? It's all about the Lagrangian, thinking about a local symmetry, invariance of the Lagrangian. And then theoretical physics, magic, inventing formulas, right? And so these are weird formulas, right? I mean, that's, to me, have you ever seen anything like that in any of your math classes? No. Maybe the first term, right? Like we study conjugation sometimes. That's conjugation, right? But what we'll see as we study fiber bundles over the next few times is that these are nothing more than the natural rules for transforming representations of a connection one form on a principal fiber bundle. When you look at how the connection one form on the principal fiber bundle descends, the transformation law between looking at it in two different coordinate systems, more or less, this is the coordinate change rule for the one form connection when you look at it on the base space. So it's fiber bundles with principal connections. I'm saying things slightly wrong, but it's not because of my education. It's because of my job and atrophying. Sadly, I wish we had a physics major here. It would have helped me not become so sad. I shut up. Thanks, guys.